Okay, this here is going to be a series of videos that I'm going to record to go through the final stretch of preparing for the AP Calculus exam. Um, I've written up a quick list of bullet points that I will share here about concepts that are essential. It's almost everything we've gone over, but I think it's helpful and maybe important to put them in perspective and kind of prioritize them so you can use this as a study guide and also just as a memory organization pattern. Okay, so let me just walk you through this list real quick, and then the second part of this video will be a brief introduction into the um, patterns of free response questions that I have categorized and organized and given you templates that are really collections of problems from AP tests over the last decades that are organized into the patterns that I've identified. And I find it helpful, again, as an organization of memory and just recognizing the pattern and therefore jumping quickly to the method that or the methods that are required to solve the particular problem that falls into these categories. Unfortunately, the multiple choice questions are kind of much more diversified. They're much harder to categorize, but so that's why I'm giving you the prioritized list of concepts here. And I want to go through this real quick. This is not organized in the order of the course or in a course system, but it's organized in order of concepts that are important to grasp and understand in calculus. So there's at first here, beginning with the fundamental theorem of calculus, the connection, understanding the connection between differential and integral calculus, which describes the relationship between derivatives, which is slope functions, and antiderivatives, which is integral area function or accumulation function, depending on the context. So this relates directly to the problems here that are up here. Let's see which one. So derivative graph problems is a direct relationship with that fundamental theorem of calculus, because in derivative graph problems, you generally are given the graph of the first derivative. And so you can read from that graph both the area under the curve, which takes you to the values of the original function, as well as the slope of the first derivative, which leads you to the second derivative. And then from there, you can determine all kinds of things, such as increasing or decreasing or concavity of the original function. And so we'll go into this in detail when we go over a specific problem of each of these categories. And that's what the video series is going to be about. So I'm going to make a playlist that has this introduction video and then a separate video where I show you the specific characteristics of each of these models. And I go through one example problem in particular and show you how to solve that and what to look for in these particular models. So then connecting a function and its derivatives, that's what I mentioned. You can find from the first derivative test if the function is increasing or decreasing. You can find from the second derivative test if it's concave up or concave down. Then you can find local extrema using the first and second derivatives. And you can find absolute extrema, where we always, when we see absolute, that should trigger that we have to consider local extrema and endpoints. So typically in questions, you will say, determine the absolute maximum or determine the maximum absolute minimum of a function. And then that is the challenge here is first finding local extrema, either maximum or minimum, depending on what's requested, what's asked. And then secondly, find the endpoints, or yeah, find both endpoints and then check the local extrema and the value of the function at the local extrema and the value of the function at the endpoints, and determine which one is absolute highest or lowest extreme. Yeah. This is where optimization problems comes into play. And in the specific application of position, velocity, and acceleration functions, that is also kind of a subset specifically taken from physics. And that is over here. Let's see, there is a particle timeline problems. That is the type of problems here, particle timeline problems, that plays into the specific iteration of this connecting a function and its derivative that is connecting position, velocity, and acceleration functions. Then another subset of that is related rates problems. Let's see, this doesn't really have its own category here because it's usually not a main topic of a free response question, although in a sense there is this differential equation problem that is kind of can play into that, and we'll go over that in particular there. Okay, so now let's look at differentiation pattern and rules. This section here of things that you need to know is digging into a review of everything that's essential in the differential calculus section. Okay, so you have to, and that's particularly useful for multiple choice questions, you have to recognize a function in limit notation. That what I'm talking about here is the definition of the derivative, right? Where the forms are limit of h as h approaches 0 of f of x plus h minus f of x over h, that format. So if they give you a problem with a specific function inserted into that f of x plus h and f of x, you have to be able to extract the function from that and then see, okay, they want me to find the derivative of this. So then I'm just going to use one of the shortcuts or rules that I know about how to differentiate that specific function that is presented in the form of the definition of a derivative. So that's an important pattern to be aware, that you don't all of a sudden start trying to solve the actual limit question there, but just recognize the pattern, recognize the notation, and solve it and find the derivative using the shortcuts and rules that we know. So then here, just to summarize and mention all of them, there's the power rule. That's just finding the derivative of a power function. Then the product rule, that's VUF, V U prime plus U V prime. Then quotient rule, also VUF, but it's V U prime minus U V prime over V squared. Then the chain rule, we've gone over this many times, so you should be really comfortable with that. Just always identify inside functions and remember to take the derivative and multiply the derivative of the outside function with the derivative of the inside function until you don't have any more. You continue that until you don't have any more inside functions. Then implicit differentiation, that's an important technique they need to review, but again, we'll apply this in problems and just kind of refer to this. Trig functions, you need to know all derivatives of trig functions, just really memorize them. Derivatives of e to the x and ln x, and I would add to that, actually, it's not often asked anymore. It's kind of like, I would say the multiple choice questions have been watered down a little bit over the years. But I would kind of also want to know what a to the x is, a derivative of that, right? How to differentiate that. Then derivatives of inverse functions, which allows you to find derivatives of inverse trig functions. So inverse trig functions are also really important to know. The derivatives of those. And then in kind of like not a very super tightly related way, I added the median value theorem here because it's important. Usually in problems that follow the table chart problems pattern. So table chart problems, that's just to summarize into a group all the problems that are giving you a function in terms in the format of a table chart, of a table of value examples. And so usually when you see a table chart problem, there will be an average rate of change asked. And you can, one of the few things that you can actually do with table chart problems is apply the median value theorem, which is to say, if there is an average rate of change, which you can simply just determine by plugging in values into the rise over run function, then there must be a specific point in the interval that we're looking at, that has a tangent line with that specific slope. So a seed where f prime of c equals the slope of that is the average slope. So that belongs into this. To note here in summary, one of the limitations of table chart problems is that you cannot determine continuous increasing, decreasing, or concavity criteria on table chart just from being given the chart of a table of some values. The reason for that is, so even though they're telling you the function is continuous and differentiable, but since you don't know if it goes further up or further down than the direct line between the values that are given, it's not possible to determine increasing or decreasing quality or concavity qualities of a function just by given the table chart problem. And they're usually trick questions that try to kind of, coax you into that, particularly in the multiple choice questions. There are sometimes problems where you think, oh, that must be true because the function is continuous and differentiable, so it must be going up over this whole period. But if you only have certain points given by a table, then you cannot make that determination. So that can usually not be said, can never be said. So then usually there the answer is looking for something that has to do with the median value theorem and find the average value, and there might be a multiple choice point answer that relates the median value theorem there. Then L'Hopital's rule, that's the if you have an indeterminate form of a derivative, you have to, or of a limit, I should say, of a limit of a function, then you can and have to take derivatives of the numerator and denominator and try to find the same limit on that new quotient. It's usually a quotient thing. And then so continue that until you get to a point where you don't have a zero in the denominator anymore. So these are derivatives. And then the rest here, or the next section, is the same kind of concepts applied to integrals. So integral patterns and rules. This first thing here is Riemann sums and the definite integral. I put the unit number here so you can have an easier time looking that up in your lessons, in the lesson worksheets, and use the box notation there, or the box entries, to refresh your memory on that in the particulars. So specifically, you need to be familiar with transcribing a definite integral to an infinite Riemann sum and vice versa. So that's where, we have patterns of that n that goes to infinity. So we'll go over that in detail. It's not the purpose of this video right here. Just to make sure that you know this and review this part is a really important thing to review, because it's always in a problem somewhere, often even in the problems that we're going to go over here in this video series. So here are now antiderivative rules. And again, see, this is not in any kind of specific order following the course material, but the antiderivative rules are in unit 6.9, summarizing here constant multiple power rule. So that's like the inverse of the power rule of the derivative power rule. Then make sure you know the antiderivatives e to the x and 1 over x. So this relates because the antiderivative of 1 over x is ln x, right? Know the antiderivatives of trig functions and inverse trig functions. And here we really only need to know, for the purpose of calculus AB, we only need to know arcsine, arccosine, and arctangent. Then U substitution, that's like the inversion of the chain rule. And we've gone over that as well. So it's very important to review this in this section. Then differential equations, unit 7. We've kind of pushed through this real fast. We will run into this in some of the problems, not necessarily for the model functions here, for the free response, because well, no, there is a specific here. There's a differential equation problems is a specific category here. But usually what's not in this is slope fields. Slope fields are frequent, or not frequent, but you can expect to see a slope field problem in the multiple choice questions. So we'll go over that. And I make some separate videos for these types of multiple choice questions as well. So then differential equations have the general solutions that are represented by slope fields, right? Because there can be several functions that satisfy the differential equation, but they are all going to be fitting into the slopes that are entered into the slope field. And then the particular solutions, they satisfy the differential equation that's given and the initial condition. And we'll go over that in detail again on this differential equation problems category and model here. All right, so then, yeah, and this is also important. I probably go over this and make a separate video again about the differential equations for exponential models, just because I think that the shortcut that I taught you in class that I haven't really found anywhere in any material, it will really help you with multiple choice questions, because for multiple choice questions, you usually don't have to show every single step of the work, and you just have to get the answer right. So with that, it's useful to know a shortcut and just not get confused and not get tangled up in the individual steps that you have to go through. So then applications of integration, that's also an important section, this whole unit 8. We also went through this really quickly, but still, let me summarize it here quickly so that you recall. So the AVT, that's the average value theorem, is always going to be asked. It's coming up in multiple iterations of the model functions here, of the model problems. And again, we'll point this out in specific problems when we run into them. Then particle motions, particle motions, as I said before here, pointed out, that has its own model of free response questions, particle timeline problems. That's particle motion. Accumulation and the definite integrals, that is part of this. It's also part of this. It's also sometimes part of this. Okay. Oh, and it also can be seen as kind of part of in and out problems. In and out problems come again a little bit later here, basically in area between curves. Area between curves in terms of x and in terms of y. So this is vertical slices would be in terms of x, and horizontal slices would be in terms of y. That is really the representation of an in and out problem in real life. So we'll go over that in detail there. Then volumes, the last three here are volumes. They're volumes with cross sections where the area between curves is used as a base of a solid, and then each cross section is described as a square or a rectangle or a triangle or a semicircle or something like that, where you just have to find a formula for each slice and turn the integral of the area, that is the base, into a formula for that slice and integrate it that way. That way you get the volume with a cross section. Then volume using disks, that is about revolving a curve around an axis of revolution. And as an expansion of that, then is the volume using washers, which is revolving an area between curves around an axis of revolution. And again, this comes from solids and integrals. Solids and integrals is all about all this stuff, okay? And we've been over problems that allow calculator use and problems that don't. And I will point this also out as we go through these different problems here. There will be some that allow calculator and some that don't. And I'll review and show you there again how to do that. And that's really an important skill, not only to know, but to practice so that you're fast with that. Using Desmos shouldn't be a problem, okay? Good. Then I have a couple of extra categories here. It's just math problems. That's kind of like problems that don't fall into any of the specific categories here. And yeah, so there will be more videos in this video series about each individual of these areas here.